Hello, in this video we're going through the AQA GCSE Chemistry 2024 Paper 1 Higher Tier, question by question. I'll show you not just the answers, but how to think through them in the way the mark scheme expects, so you know exactly how to pick up marks in the exam. If you can, pause and try each question before watching the explanation. That's where the real learning happens. If you're looking for a chemistry tutor and would like some extra support with your studies, I leave a link to my website about my tutoring services on the description. Feel free to take a look. Let's get started. In question 1, we have a method used by a student to produce a salt by reacting copper carbonate with sulfuric acid. The method is 1. Measure 50 cubic centimeters of sulfuric acid into a beaker. 2. Add copper carbonate powder. 3. Stir the mixture. 4. Repeat steps 2 and 3 until copper carbonate is in excess. 5. Filter the mixture. 6. Warm the filtrate gently until crystals start to appear. 7. Leave the solution to cool and crystallize. For question 1.1, we are asked to complete the word equation in which copper carbonate reacts with sulfuric acid to produce carbon dioxide and 2 other products. We know that when a carbonate reacts with an acid, the products are always a salt, water, and carbon dioxide. Since carbon dioxide is already given, one of the remaining products must be water. To identify the salt, we look at the acid involved. Sulfuric acid produces sulfate salts. The positive ion in copper carbonate is copper, so the salt formed contains copper ions and sulfate ions. Therefore, the other product is copper sulfate. In question 1.2, we need to find one observation that proves the copper carbonate is in excess during step 4. There are 2 correct answers you could give here. First, you could say that the solid stops dissolving. This means you'll see the copper carbonate powder settle and remain at the bottom of the beaker, even after stirring. Alternatively, you could note that the effervescence stops. Because all the acid has completely reacted, the fizzing stops since no more carbon dioxide gas is being produced. In question 1.3, we need to give a reason for filtering the mixture in step 5. Filtering will remove any excess of copper carbonate, leaving the solution with dissolved copper sulfate. In question 1.4, we need to name the equipment that can be used to warm the filtrate gently in step 6. The key word is gently. The filtrate can be warmed gently using an electric heater or a water bath. These methods provide controlled heating and are preferred to a direct flame such as a Bunsen burner. Be really careful here, less than half of students got this mark because they simply wrote a Bunsen burner. The exam board rejected a Bunsen burner on its own because its flame is too intense for the gentlest heating. To get the mark using a Bunsen burner, you would have to explicitly say you were using it to heat a beaker of water, which just creates a water bath anyway. In question 1.5, we have that the maximum theoretical mass of the salt that could be produced using 50 cubic centimeters of the sulfuric acid is 12.5 grams. The percentage yield of the salt is 92.8%. We are asked to calculate the mass of salt actually produced using the equation provided. Replacing the values given in the formula and rearranging terms, I get 11.6. So the answer is 11.6 grams. Note that we have not used the 50 cubic centimeters data given. In questions 1.6, we have that some salts can be produced by reacting sulfuric acid with a metal. Neither copper nor sodium is used to produce a salt with sulfuric acid. We need to give one reason why each metal is not used. Copper is too unreactive. It sits below hydrogen in the reactivity series, meaning it will not react with dilute sulfuric acid at all, and no salt will be produced. Sodium is too reactive. It sits near the very top of the reactivity series, making the reaction with sulfuric acid extremely violent and explosive. Question 2 is about the periodic table. Sodium and potassium are in group 1 of the periodic table. In question 2.1 we need to give one similarity and one difference between the electronic structures of sodium and potassium. The electronic configuration of sodium is 281 and potassium is 2881. Comparing these, we can see that the similarity is that both have one electron in their outer shell. The difference is that the sodium has 3 shells but potassium has 4 shells. In question 2.2, we need to give 2 observations made when potassium reacts with water. When you drop potassium into water, it reacts violently. It melts into a ball, floats, and moves around very quickly on the surface. It also ignites with a characteristic lilac flame, fizzes rapidly, and quickly disappears, sometimes ending with a small explosion. To get both marks, you just need to pick any 2 observations from this list, such as effervescence or bubbles, fizzing, potassium floats, moves around, becomes smaller or melts, flame or explosion. Moving on to question 2.3, we are told that potassium hydroxide solution is produced from this reaction. We need to state the color of universal indicator when it's added to this solution and give a reason why. Universal indicator changes color depending on pH, ranging from red for acids to purple for alkalis. Because potassium hydroxide is a strong alkaline solution, the universal indicator will turn purple, violet, or blue, depending on how concentrated it is. So, the answer is purple, violet, or blue, because the solution is alkaline. For question 2.4, we need to plot the data from Table 1 onto the graph in Figure 1. Looking at the table, we have 5 complete data points to plot using their atomic number on the x-axis and their density on the y-axis. We will leave krypton out because its density is marked as x. For the plots, always use small, sharp crosses rather than tiny dots. The examiners mark these on scan digital images, and small dots can easily disappear on a screen, making it incredibly hard to see your hard work. For question 2.5, we need to estimate the density of krypton using both Figure 1 and Table 1. If you look at the points plotted on the graph, you can see they follow a clear linear trend, meaning our line of best fit should be a straight line. There are 2 easy ways to solve this. The first approach is using the graph. If you draw a straight line of best fit through the points, you can find 36 on the x-axis, which is krypton's atomic number, and follow it up until it hits your line. Reading across to the y-axis gives us a density of 3.5. The second approach is purely mathematical. If you look closely at the atomic numbers, krypton at 36 is exactly halfway between argon at 18 and xenon at 54. Because the trend is linear, we can assume its density will also be exactly halfway between theirs. If we take argon's density of 1.6, add xenon's density of 5.4, and divide by 2, we get 3.5. Either method works perfectly. The mark scheme is quite generous here and allows any value between 3.0 and 3.8. Let's look at question 2.6, which focuses on the group 7 elements, the halogens. The question reminds us of the core rule: a more reactive halogen can displace a less reactive halogen from a solution of its salt. We are asked which of the 4 combination of solutions will produce a reaction when mixed. To solve this, we just need to remember the trend: reactivity increases as you go up group 7. So, a standalone halogen can only cause a reaction if it sits higher on the periodic table than the halogen inside the salt. Let's quickly check the choices. In the first option, chlorine is below fluorine, so nothing happens. In the second option, chlorine is above bromine on the periodic table. Because chlorine is higher up, it is more reactive and will successfully displace the bromine. This means a reaction will happen here. Just to double-check the others, in options 3 and 4, bromine is below both fluorine and chlorine, meaning it isn't reactive enough to cause a displacement. Therefore, the correct choice to tick is the second box, chlorine and potassium bromide. In question 2.7, we need to identify the correct trends as we move down group 7 of the periodic table about relative molecular mass and boiling point. The correct choice is the final option, relative molecular mass increases and boiling point increases. Here is why. First, as you go down group 7, the atoms gain more protons and neutrons, which means their relative molecular mass increases. At the same time, they also gain more electron shells. Having more electrons means the intermolecular forces between the molecules, known as van der Waals forces, become much stronger. More energy is needed to break these forces, which is why the boiling point increases as well. Question 3 is a classic exam question on the history of the atom. We'll look at what the examiners are looking for the 6 marks. Question 3.1 asks us to name the 2 early models of the atom shown in Figure 2. Model A shows a single ball of positive charge with negative electrons dotted throughout it. This is the plum pudding model, discovered by J.J. Thomson. Model B shows electrons orbiting a central positive charge in fixed rings. This is the Bohr model, or the nuclear model. Top examiner tip: while the exam board accepted a nuclear model here, the examiner's report noted that Model B specifically shows electrons in fixed orbits, which is Niels Bohr's adaptation. Avoid just writing atomic model or modern model, be specific to get the 2 marks. Question 3.2 is a 4-mark extended answer question asking us to compare Model A with the modern atomic model we use today. Before we write anything, let's look at what the examiners said about this specific question. To get into the top marks tier, you must do 2 things. First, mention a similarity as well as differences. Second, write a true comparison. Don't just describe Model A and then describe the modern model separately, compare them. The best way to lay out your answer for the examiner is actually a simple table. Let's start with our similarity. Both models contain negative electrons, and both models are completely neutral overall. A common mistake is thinking the plum pudding model has a positive charge. It doesn't. The positive ball is balanced by the negative electrons. Now for the differences. First, Model A is a solid ball of positive charge with no empty space. The modern model is mostly empty space. Second, Model A has its mass spread evenly throughout the whole atom. In the modern model, almost all the mass is concentrated right at the center. Third, Model A has no nucleus, protons, or neutrons. The modern model has a distinct central nucleus containing protons and neutrons. Finally, in Model A, electrons are distributed randomly. In our modern model, electrons are organized neatly into shells or energy levels. Include at least 1 similarity and 3 of those direct differences, and you've secured an easy 4 marks. In question 3.3, we are asked to define the term isotopes, referring to subatomic particles in our answer. To get full marks on an isotope definition, your answer must be a strict 3-part checklist. Part 1, you must state they are atoms. Part 2, they are of the same element, or with the same number of protons. Part 3, you must say they have a different number of neutrons, or a different mass number. As we need to mention subatomic particles in our answer, put it together: isotopes are atoms of the same element with a different number of neutrons. Question 4 is a classic question based on required practical for investigating the energy change in a reaction. Specifically, the reaction between zinc and copper sulfate solution. In the question, a student measured the maximum temperature observed when 25 cubic centimeter portions of copper sulfate solution had zinc added to them. The results are provided in a graph in Figure 3, showing the mass of zinc added on the x-axis, and the highest temperature reached in degrees Celsius on the y-axis. Question 4.1 asks us to draw 2 lines of best fit on Figure 3, and specifies that the lines should cross. This is worth 2 marks, but according to the examiner's report, less than half of students got this completely right. Let's make sure you aren't one of them. To score both marks, you need to draw 2 straight lines. For your first mark, draw a straight line of best fit through the first 5 points, starting from the point 0.0021 up towards 0.80, 47. You want an even scatter of points on either side of your ruler. For your second mark, draw a horizontal line of best fit through the last 4 points, which sit around the 46 to 47 degree mark. Notice that point at 1.20 grams that dips down a bit? That is an anomaly. Ignore it and draw your straight line through the remaining flat points. Ensure your 2 straight lines clearly intersect or cross over right around the 0.80 gram mark. In question 4.2, we are asked to explain the results, not including the anomalous results. The examiner noted that many students lost marks here because they only described what happened, rather than explaining the chemistry behind it. Let's break it down into 4 distinct, mark-earning points. Point 1. Explain the initial temperature rise. As we add more zinc up to 0.8 grams, the temperature rises because the reaction is exothermic, meaning energy is being transferred to the surroundings. You must mention the word exothermic or energy transfer to get this mark. Point 2. State the turning point using data. The temperature stops rising at 0.80 grams of zinc, at around 47 degrees Celsius. Point 3. Explain the plateau. After 0.80 grams of zinc is added, there is no further temperature increase because no additional reaction is taking place. Point 4. Explain why the reaction stopped. This is because all the copper sulfate solution has been completely used up. At this stage, the zinc is now in excess, and the copper sulfate was the limiting reactant that ran out. So, a concise answer that would score all 4 marks is: the temperature rises because the reaction is exothermic and transfers energy to the surroundings. The temperature increases until about 0.8 grams of zinc is added, reaching approximately 47 degrees Celsius. After this, the temperature remains constant because no further reaction occurs. This is because the copper sulfate has been completely used up, and the zinc is now in excess. Moving on to question 4.3. We are asked to explain why using a polystyrene cup gives more accurate results than using a glass beaker. This question is worth 2 marks, but the examiner's report reveals that fewer than a quarter of students managed to score both marks. Let's look at why so many missed out, so you don't make the same mistakes. The key here is comparison. Many students lost marks because they stated that polystyrene is an insulator and glass is a conductor. In reality, both materials insulate and conduct heat, just to different degrees. To secure your first mark, you must use comparative language and state that polystyrene is a better thermal insulator than glass. Alternatively, you could say glass is a poorer insulator. For the second mark, you need to explain the impact of this. Because polystyrene is a better insulator, there is less energy transfer to the surroundings. Be careful with your wording here too. The examiner noted that many students incorrectly claimed that no energy is lost when using polystyrene. Some energy is always lost, so ensure you say less energy is transferred or lost to the surroundings. Now, let's look at question 4.4. We need to complete the ionic equation for the reaction between zinc and copper sulfate solution, including the state symbols. This is another 2-mark question. On the left side of the equation, we have zinc solid plus a copper 2 plus aqueous ion. Because zinc is more reactive than copper, a displacement reaction takes place. The zinc displaces the copper, donating electrons to it. This means on the right side, the products are a zinc 2 plus ion, which is aqueous, and pure copper, which is a solid. Let's move on to question 4.5. We are given a table with 4 different trial results for the highest temperature reached, and we need to calculate 2 things, the mean highest temperature and the uncertainty. This question is worth 3 marks. While most students successfully calculated the mean, fewer than half managed to get the uncertainty correct. Let's make sure you get all 3 marks. To find the mean temperature for your first 2 marks, add the 4 values together, 37.6 plus 37.2 plus 37.8 plus 37.4. And divide the results by the number of trials, which is 4, till you get a mean temperature of 37.5 degrees Celsius. For the third mark, we need to calculate the uncertainty. The uncertainty is half of the total range. The range is obtained by taking the highest value in the table, 37.8, and subtracting the lowest value, 37.2. Then, the range is divided by 2, giving an uncertainty of 0.3. So, the final answer to write on the dotted line is 37.5 plus or minus 0.3. Finally, let's look at question 4.6. We are told that the results show random errors, but the student did not make any measuring errors. We need to suggest one reason for these random errors for 1 mark. This question tripped up over 3/4 of students. The examiner reported that many students completely ignored the prompt and incorrectly listed a measurement error anyway. Because the question rules out measuring errors, have a look closely at the physical experiment itself. What variables are hard to keep perfectly identical every single time? You can score this mark by giving any one of the following reasons. First, the starting temperature of the solution may have been slightly different for each trial. Second, the stirring of the mixture could have been inconsistent. Or third, there may have been an inconsistent use of a lid on the polystyrene cup, letting different amounts of heat escape each time. Now, you might notice that a lid wasn't actually mentioned in the student's method steps. However, AQA accepted the inconsistent use of a lids as a correct answer because they are testing your broader knowledge of required practical 4. When you did this practical in school, you likely used a lid to stop heat escaping. Mentioning variables like inconsistent stirring or starting temperatures is the perfect way to secure this final mark. Let's tackle question 5.1. This question is about ionic compounds and electrolysis. We are told that calcium and chlorine react to produce calcium chloride. We need to describe what happens to calcium atoms and chlorine atoms when this ionic compound is formed. This is worth 4 marks, but according to the examiner's report, only 1 in 8 students scored full marks. Over a third of students scored 0 due to a total lack of precise scientific language. Let's make sure you don't fall into the same traps. To get your first 2 marks, you need to describe exactly how the electrons move. First, state that each calcium atom loses 2 electrons. Second, state that each chlorine atom gains 1 electron. The examiner noted that many students simply said calcium loses electrons and a chlorine gains electrons. If you don't specify the exact numbers, you score 1 mark instead of 2. For the third mark, you must explain the ratio of the atoms reacting. Because calcium loses 2 electrons, but a chlorine atom can only take 1 calcium atom must react with 2 chlorine atoms. For your fourth and final mark, describe what is formed as a result. You must explicitly state that this forms calcium ions and chloride ions. So, a 4 marks answer could be, each calcium atom loses 2 electrons, and each chlorine atom gains 1 electron. This means 1 calcium atom reacts with 2 chlorine atoms, forming calcium 2+ ions, and chloride- ions, which both have full outer shells. The examiner raised some red flags. Although the question asked to describe what happens to atoms of calcium and chlorine, many failed to include the word atoms when referring to calcium and chlorine. Calcium and chlorine refer to the elements in bulk, not to individual atoms. Many students incorrectly referred to the product as chlorine ions. Remember, when chlorine gains an electron, its name changes to a chloride ion. Also, some students correctly described the transfer of electrons, but then accidentally said the atoms share electrons. Sharing is covalent bonding, but this is strictly ionic bonding. Let's move on to question 5.2. We are told that solid calcium chloride cannot be electrolyzed, and we need to give one reason why. This is worth 1 mark, but only 2/5 of students got it right. Electrolysis requires an electric current to flow through the substance. For a current to flow, you must have charged particles that are completely free to move around and carry that charge. In solid calcium chloride, the calcium and chloride ions are locked inside a giant ionic lattice. They can't move to the electrodes. So, your mark-earning answer is simply, the ions cannot move, or the ions are in fixed positions. The examiner's report highlighted some misconception here. Many students wrote that electrons cannot move. Remember, in electrolysis, it's the movement of ions that carries the current through the liquid, not electrons. Other students simply stated that the substance needs to be molten or dissolved, which is true, but that doesn't explain why. Now, let's look at question 5.3. Name the product formed at the negative electrode when aqueous calcium chloride solution is electrolyzed. This is another 1 mark question that tripped up over half of the students. The key word is aqueous. This means we don't just have calcium and chloride ions in the beaker, the water molecules also split up into hydrogen ions and hydroxide ions. At the negative electrode or cathode, the positive ions compete to gain electrons. Our positive ions are calcium and hydrogen. The rule for the cathode is simple, the least reactive element gets discharged. Because hydrogen is much less reactive than calcium, the hydrogen gain electrons to form hydrogen gas. So, the correct answer is hydrogen. Let's look at question 5.4. We need to identify the correct half equation for the reaction at the positive electrode when aqueous calcium chloride solution is electrolyzed. We have 4 options, and it's worth 1 mark. The positive electrode, or anode, attracts negative ions, producing oxidation. We can discard option 2 and 4, because there are reductions and there are no negative ions on the left-hand side of the reaction. In our aqueous calcium chloride solution, we have 2 negative ions competing, chloride ions from the salt and hydroxide ions from the water. The rule for the positive electrode is straightforward. If halide ions are present, like chloride, bromide, or iodide, they will always win the race and get discharged. Because we have chloride ions here, they win, meaning chlorine gas will be our product. This immediately rules out the third option, leaving us with the first option as the right answer. Let's move on to question 5.5. A student investigates the electrolysis of a green copper chromate solution by placing a single drop of it onto filter paper soaked in an electrolyte. Figure 5 shows the results after the power supply is turned on. A blue color spreads toward the negative electrode, and a yellow color spreads toward the positive electrode. We are asked to explain these results based on the ions present. First, let's look at the colors. The starting solution is green because it's a mixture of 2 differently colored ions. For your first mark, you must state that copper ions are blue and chromate ions are yellow. The examiner noted that many students mistakenly said copper is blue or chromium oxide is yellow. Remember, the uncharged metals or compounds aren't responsible for the color here, it is specifically the ions themselves that have these colors. For the second mark, look at the negative electrode, or the cathode. Opposite charges attract. Because copper 2+ ions carry a positive charge, they are attracted to and move toward the negative electrode. This is why a blue smear appears on the left side of the paper. For the third mark, look at the positive electrode, or the anode. The chromate ion has a 2- negative charge, meaning it is attracted to and moves toward the positive electrode. This explains why a yellow smear appears on the right side. So, a full mark written answer is, copper ions are blue and chromate ions are yellow. The positively charged copper ions move toward the negative electrode, while the negatively charged chromate ions move toward the positive electrode. In question 6.1, a student is investigating the voltage produced by different pairs of metal electrodes in a chemical cell. They are using a fixed nickel electrode as a baseline, and changing the second electrode, called electrode A, using 5 different metals: copper, magnesium, nickel, silver, and zinc. Table 3 shows us the resulting voltages. We need to write the symbols of these 5 metals in order from most reactive to least reactive, and then justify our answer. A chemical cell produces a voltage because different metals have different tendencies to lose electrons. The further apart 2 metals are in the reactivity series, the greater the difference in their ability to lose electrons, and the larger the voltage produced. In this experiment, nickel is our fixed reference point, which is why the nickel versus nickel cell reads exactly 0.00 volts. Metals that are more reactive than nickel will push electrons away more strongly, giving us a positive voltage. The more reactive the metal, the higher that positive voltage will be. Looking at the data, magnesium gives a high positive voltage of 2.12 volts, and zinc gives a positive voltage of 0.51 volts. This means magnesium is the most reactive, followed by zinc. Next comes our baseline, nickel, at 0 volts. Metals that are less reactive than nickel will produce a negative voltage. The less reactive the metal, the more negative the voltage becomes. Copper gives a reading of -0.59 volts, while silver drops even lower to -1.05 volts. This tells us copper is less reactive than nickel, and silver is the least reactive of them all. This order will give you the first 2 marks. For your third mark, you need to provide the justification. You must state that the higher the positive voltage, the more reactive the metal is. Now let's tackle question 6.2. This is a 6-mark extended response question that requires us to plan an experiment. We need to investigate how the voltage produced by a chemical cell varies with the concentration of the electrolyte solution. We are told we have the metal electrodes from Table 3, a 1.0 mol per decimeter cubed sodium chloride solution, and pure water available. 6-mark questions are marked using levels. To hit level 3 and secure 5 to 6 marks, your method must be a logically sequenced, valid plan that explains exactly how to change your independent variable and how to keep everything else a fair test. First, let's understand the science of what we are altering. We need to test different concentrations of our electrolyte. We have a starting stock solution and pure water. To create different concentrations, we perform a process called dilution. By mixing different measured volumes of the sodium chloride solution with different volumes of pure water, we can create a range of concentrations. The examiner noted a major pitfall here. Many students vaguely mentioned adding amounts of water rather than specifying volumes, and failed to clearly state that you must mix both the sodium chloride solution and water together. Next, let's look at our control variables to ensure a fair test. Since we are investigating how concentration affects voltage, everything else must stay exactly the same. First, you must use the same 2 metals as electrodes for every single test. A massive mistake made by many students was thinking they needed to swap out and test all the different metals from the previous question. Pick 2 metals, for example, magnesium and copper, and stick with them. Second, you must keep the total volume of the electrolyte solution identical in every test. Finally, ensure you don't confuse a chemical cell with an electrolysis setup. The examiner warned that several students mistakenly included a power supply in their plan. A chemical cell generates electricity from chemical energy, so you absolutely do not use a power supply. You simply connect your 2 electrodes directly to a voltmeter to measure the voltage produced. So, here is a logically sequenced, step-by-step plan that guarantees all 6 marks. Step 1. Use a measuring cylinder to measure a specific volume of the 1.0 mol per cubic decimeter sodium chloride solution, and a specific volume of pure water. Mix them in a beaker to create your first diluted concentration. Step 2. Pour a fixed total volume of this solution into your cell setup. Step 3. Select 2 different metal electrodes from Table 3, such as magnesium and zinc, and place them into the solution. Step 4. Connect the electrodes to a voltmeter and measure and record the voltage produced. Step 5. Repeat the entire process at least 4 more times, using different measured volumes of sodium chloride solution and water to vary the concentration. Step 6. Ensure that for every repetition, you use the exact same 2 metals for the electrodes and maintain the same total volume of electrolyte solution. We move to question 6.3. This question is simple. Describe how a hydrogen fuel cell produces a potential difference. According to the examiner's report, only 1 in 25 students scored both marks here. That means a massive 96% of students missed out on full marks for what is actually a straightforward specification point. Let's make sure you aren't one of them. To understand the answer, we need to look at what is happening inside the fuel cell. A hydrogen fuel cell generates a potential difference, which is just the scientific term for voltage, by reacting hydrogen gas with oxygen gas. Inside the cell, hydrogen molecules are fed into one side. Here, the hydrogen is oxidized, meaning that it loses electrons turning into hydrogen ions. These lost electrons cannot pass straight through the middle of the cell. Instead, they are forced to travel through an external circuit. This movement of electrons through the wire is what creates the electric current and the potential difference. Eventually, those electrons arrive at the other side of the cell, where they combine with oxygen gas and the hydrogen ions to produce water. Water is the only waste product of this clean energy reaction. To get both marks, your answer needs 2 distinct points. Mark 1, state that hydrogen is oxidized, or that hydrogen loses electrons. Mark 2, state that this reaction produces water. Put that together into a neat sentence. Hydrogen is electrochemically oxidized by losing electrons, and it reacts to produce water. That is an instant 2 marks. The examiner noted a few very common mistakes that cost students their marks. Let's break down what not to say. Pitfall 1. Confusing reactants. Many students wrote that hydrogen ions react at the start. This is incorrect. The reactant fed into the cell is hydrogen gas, which consists of hydrogen molecules. The ions are only formed after it loses electrons. Pitfall 2. Saying it burns. Do not mention combustion or burning. While burning hydrogen also makes water, a fuel cell operates electrochemically without a flame. If you mention combustion, you will lose the mark for oxidation. Pitfall 3. The turbine myth. A lot of students guess that the cell works like a traditional power station by creating steam to turn a turbine which drives a generator. Hydrogen fuel cells do not have moving parts, they generate electricity directly from the chemical reaction. Moving on to question 7, which is all about the metal iron. Question 7.1 asks us to describe how iron conducts thermal energy. This is worth 2 marks. Looking at the examiner's report, only a quarter of students managed to score both marks here, and a massive 1/3 of students scored 0. Let's look at why so many students missed out, and how you can lock in these marks easily. To understand why metals are such fantastic conductors of heat, we need to picture their giant structure. Iron, like all metals, consists of a lattice of positive metal ions arranged in regular layers. Surrounding these positive ions is a sea of delocalized electrons. These electrons are free to move throughout the entire structure. When you heat one end of a piece of iron, the particles gain thermal energy. In a non-metal solid, heat is only passed along because the atoms vibrate and bump into their neighbors. This takes time. But in a metal, we have a secret weapon, those delocalized electrons. When they gain thermal energy, they move much faster. Because they are free to travel through the lattice, they rapidly move from the hot end of the metal to the cooler end, colliding with positive ions along the way and transferring that thermal energy throughout the structure much quicker than vibrations alone could ever manage. To get the full 2 marks from the AQA mark scheme, your description needs 2 clear components. Mark 1, state that thermal energy, or heat, is transferred. Mark 2, state that this transfer happens by delocalized electrons. A concise, perfect answer would be thermal energy is transferred through the structure by delocalized electrons. Let's look at the mistakes highlighted in the examiner's report so you can avoid them. Pitfall 1. Describing standard solids instead of metals. A lot of students just wrote about general conduction in solids, saying that particles vibrate and pass energy to neighboring particles. While this does happen in metals, it's not the main reason metals are such good conductors. The examiner specifically wanted you to focus on what makes metals unique, the delocalized electrons. Pitfall 2. Explaining electricity instead of heat. Many students spotted the phrase delocalized electrons in their memory banks but accidentally described electrical conductivity instead of thermal conductivity. Make sure you don't talk about electrons carrying a charge or flowing in a circuit. Keep your focus entirely on the transfer of thermal energy or heat. Pitfall 3. Reusing the word conduct. The question asks you how iron conducts. If you just write delocalized electrons conduct the heat, you haven't actually explained the mechanism. Use the word transferred or moved to clearly show the examiner you understand the process. Next up is question 7.2, and it's a classic 3-mark question that comes up all the time in AQA exams. The question states, pure iron is too soft for many uses. Explain why mixing iron with other metals makes alloys which are harder than pure iron. Over half of students managed to score 2 or 3 marks here, which is decent, but many missed out on the full 3 marks simply due to poor choice of words. Let's break down exactly how to write a flawless, full-mark answer. To understand why alloys are harder, we need to compare the atomic structure of a pure metal to that of a mixture. In a sample of pure iron, all the iron atoms are exactly the same size. Because they are identical, they arrange themselves into a neat, regular lattice with distinct, orderly layers. When you apply a force to pure iron, these smooth layers can easily slide over one another. This ability to slide is exactly what makes pure iron relatively soft and malleable. An alloy, however, is a mixture of different elements. When you mix iron with a different metal, you are introducing atoms of a different size into the lattice. These new, differently sized atoms disrupt the neat, regular arrangement. They distort the straight layers, turning them into a jagged, uneven structure. Because the layers are now distorted, they can no longer smoothly slide past each other when a force is applied. This locked structure makes the material much harder and stronger. To get all 3 marks on your paper, your explanation must follow this exact 3-step logical chain. Mark 1. State that the alloy contains different sized atoms. Mark 2. Explain that this means the layers are distorted. Mark 3. Conclude that because of this distortion, the layers cannot easily slide over each other. If you write, alloys contain atoms of different sizes, which distorts the regular layers so they cannot easily slide over each other, you have just bagged yourself a perfect 3 out of 3. The examiner's report flagged a few very specific vocabulary errors that caused students to drop marks. Avoid these pitfalls. Pitfall 1. Blaming the bonding. A very common mistake was students trying to explain that alloys are harder because they have stronger ionic or covalent bonds. Remember, alloys still have metallic bonding. The hardness is purely down to the physical geometry of the distorted layers, not a change in bonding type. Pitfall 2. Lazy language. The examiner noted that many students said the metals are different sizes, rather than the atoms or positive ions. You must specify that it is the atoms that are different sizes. Also, don't say the atoms have different shapes. Atoms are always considered spherical in this context. Pitfall 3. The particles and intermolecular trap. Avoid using the generic word particles here, as it's too vague for the mark scheme. Stick strictly to atoms or ions. Additionally, quite a few students mentioned intermolecular forces. Intermolecular forces only exist between small covalent molecules. There are absolutely no intermolecular forces in a giant metallic lattice. In question 7.3, we're told that 0.12 moles of iron react with 0.18 moles of chlorine. We need to choose the correct balanced equation from the 4 options. According to the examiner's report, only just over half of students answered this correctly. Let's see how to solve it quickly. The key is to use the mole ratio. We're given 0.12 moles of iron and 0.18 moles of chlorine. To find the simplest ratio, divide both numbers by the smaller value, which is 0.12. For iron, 0.12 divided by 0.12 equals 1. For chlorine, 0.18 divided by 0.12 equals 1.5. So the ratio is 1 to 1.5. Chemical equations use whole numbers, so we can't leave the ratio as a decimal. We multiply both numbers by 2, giving a ratio of 2 to 3. That means 2 moles of iron react with 3 moles of chlorine. Looking at the 4 options, only the fourth equation has this ratio. So the correct answer is the fourth option. A common mistake was choosing first reaction. Students recognized a familiar reaction but ignored the mole ratio given in the question. In these questions, always use the numbers in the question first. They tell you which balanced equation is correct. In question 7.4, we need to find the ratio of the ions in Fe3O4. We're given 4 possible answers, and we need to choose the correct one. According to the examiner's report, only 2/5 of students got this question right. That means around 60% of students lost this mark. Let's look at the chemistry trick that makes this question much easier. The compound is Fe3O4, which is commonly called magnetite. At first glance, the formula looks a bit unusual because iron normally forms either Fe2+ ions or Fe3+ ions. It can't have a charge somewhere in between. The secret is that Fe3O4 is a mixed oxide. It contains both Fe2+ ions and Fe3+ ions in the same crystal structure. To work out the correct ratio, we use the golden rule of ionic compounds. The total positive charge must equal the total negative charge, so the overall charge is 0. Let's start with the oxygen ions. There are 4 oxide ions, and each oxide ion has a charge of 2-. 4 multiplied by -2 gives a total charge of -8. That means the 3 iron ions must have a total charge of +8 to balance it. Now let's test the possible combinations. If we have 2 Fe2+ ions and 1 Fe3+ ion, the total positive charge is 2 + 2 + 3, which equals +7. That doesn't balance the -8, so it can't be correct. Now try 1 Fe2+ ion and 2 Fe3+ ions. The total positive charge is 2 + 3 + 3, which equals +8. That perfectly balances the -8 from the oxide ions. So the correct ratio is 1 Fe2+, 2 Fe3+, for O2-, which is the second answer. Let's look at the traps that caught out so many students. The examiner reported that the most popular wrong answer was 3 Fe2+, for O2-, followed closely by 3 Fe3+, for O2-. These answers correctly count the number of iron and oxygen atoms, but they completely ignore the charges. In ionic compounds, counting the atoms isn't enough. You must always check that the total positive charge equals the total negative charge. That's the key idea to remember for any question like this. We move to question 7.5. We need to calculate the percentage by mass of iron in Fe3O4. We are given the relative atomic masses of oxygen and iron. Over 3/4 of students managed to score full marks on this question. It's a great place to pick up easy marks if you know the formula. Let's look at the mathematical steps to get you those 3 marks. The first step is to calculate the relative formula mass of Fe3O4. There are 3 iron atoms, so their total mass is 3 × 56, which equals 168. There are 4 oxygen atoms, so their total mass is 4 × 16, which equals 64. Now add these together. 168 plus 64 equals 232. So the relative formula mass of Fe3O4 is 232. This is your first mark. Next, we work out what fraction of that mass comes from iron. The total mass of the iron atoms is 168, so we calculate 168 divided by 232, multiplied by 100. This gives 72.4%, which is the correct answer. Even though 3/4 of students got this right, the examiner's report noted a few simple mistakes that completely ruined some students' chances of getting any credit. Pitfall 1. Forgetting to multiply by the subscript. A common error was dividing the mass of just one iron atom by the total mass, writing 56 over 232 times 100. Remember, there are 3 iron atoms in Fe3O4. You must calculate the percentage for all the iron present, not just a single atom. Pitfall 2. Not showing your working. The examiner stated that it was sometimes difficult to award any credit if a student got the final answer wrong because they hadn't explicitly written down how they evaluated the total formula mass. Always write down the total formula mass separately. Even if you make a calculation error later, you can still get a mark for a correctly calculated value based on your working. Pitfall 3. Reusing numbers from previous questions. Some students tried to use the numbers from question 7.3, which were completely unrelated. Let's take a look at question 7.6. The question states, iron 3 oxide, Fe2O3, reacts with carbon to produce carbon dioxide. We are given the balance symbol equation. Our task is to calculate the volume of carbon dioxide gas at room temperature and pressure produced from 40 kilograms of iron oxide using excess carbon. We are given the relative formula mass of iron oxide as 160, and we are told that the volume of 1 mole of any gas at room temperature and pressure is 24 cubic decimeters. This question worths 5 marks. A note from the examiner's report. A common mistake students made was trying to find a gas volume for iron oxide itself. Remember, always check the state symbols in the equation. Iron oxide has an S for solid, while carbon dioxide has a G for gas. You can only apply the 24 cubic decimeters rule to gases. Our first goal is to figure out how many moles of iron oxide we are starting with. We begin with a mass of 40 kilograms. Because our relative formula mass is based on grams, we need to convert kilograms to grams first. We start with 40 kilograms. We multiply by 1,000 grams per kilogram to cancel out the kilograms, leaving us with 40,000 grams. That conversion earns you your first mark. Next, to cancel out grams and move to moles, we divide those 40,000 grams by 160 grams per mole. 40,000 divided by 160 gives us exactly 250 moles of iron oxide. That is your second mark. Now, we need to link our reactant, iron oxide, to our product, carbon dioxide. For this, we look directly at the coefficients, the big numbers, in our balanced equation. The equation tells us that 2 moles of Fe2O3 will produce 3 moles of CO2. Therefore, we multiply our 250 moles of iron oxide by 3 moles of carbon dioxide and divide by 2 moles of iron oxide. This gives us 375 moles of carbon dioxide gas. Successfully applying this ratio secures your third mark. Finally, we need to convert these 375 moles of carbon dioxide gas into a volume. Our final conversion factor comes from the rule that 1 mole of any gas at room temperature and pressure occupies exactly 24 cubic decimeters. We take our 375 moles of carbon dioxide and multiply it by 24 cubic decimeters per mole. This equals to 9,000. Our final answer is 9,000 cubic decimeters. That completes the calculation, earning you the remaining 2 marks for the method and the final correct value. Moving on to question 8, part 1. This question focuses on propane, Cr3H late. We are provided with figure 7, which shows the displayed structural formula of propane, revealing 3 carbon atoms linked together, surrounded by 8 hydrogen atoms. The question asks us to explain why propane has a low boiling point. This is worth 3 marks, which means we need a logical, 3-step explanation to get full credit. Let's break down exactly how to secure each mark, and more importantly, look at the common traps that caught out most students. For our first mark, we need to look at the structure and classify what type of substance propane is. Propane is a small molecule, also called a simple molecule. Just stating that it is a small molecule earns you your first mark. Surprisingly, the examiner's report noted that most students completely forgot to mention the structure at all. Now for the second mark. Because propane exists as small individual molecules, what holds them together in a liquid? It is the forces between the separate molecules, known as intermolecular forces. For your second mark, you must state that these intermolecular forces are weak. For the third and final mark, we connect this back to thermal energy. Because these intermolecular forces are weak, they require very little energy to overcome. So, putting it all together for a flawless 3-mark answer, number 1, propane is a small molecule. Number 2, it has weak intermolecular forces between the molecules. Number 3, these forces require little energy to overcome. But wait, let's look at why only 1 in 7 students actually managed to get all 3 marks on this question. This is where clear and precise chemical language is absolutely critical. A massive number of students wrongly claimed that propane has covalent bonds that are weak, or that you have to break the covalent bonds to boil it. This is a huge misconception. The covalent bonds inside the propane molecule are incredibly strong and they do not break when propane boils. When propane turns from a liquid to a gas, the molecules stay completely intact. It is only the weak intermolecular forces between the separate molecules that are being overcome. The examiners explicitly stated they would not accept answers mentioning the breaking of covalent bonds. Also, be careful not to say intermolecular forces between atoms. Intermolecular means between molecules. Avoid the covalent bond trap, use the exact term intermolecular forces, and you'll easily pocket all 3 marks. Let's take a look at question 8.2. The question states, propane reacts with oxygen to produce carbon dioxide and water. The reaction is exothermic. We are shown figure 8, which contains 4 different reaction profiles labeled A, B, C, and D. Our job is to choose the single correct profile that has the right layout and the correct labels. This is worth 1 mark, but it tests 2 very important concepts, identifying an exothermic profile and identifying the correct energy arrows. The absolute first word you need to spot in this question is exothermic. An exothermic reaction is one that releases heat energy to the surroundings. Because energy is released, the products will always end up with less chemical energy than the reactant started with. Looking at our 4 options, look closely at the starting and ending lines. In profiles C and D, the product's line at the end is higher than the reactant's line at the start. That represents an endothermic reaction, which absorbs energy. Because our reaction is exothermic, we can instantly eliminate C and D. This leaves us with a choice between A and B. Both profiles show the correct exothermic shape, where the products are lower than the reactants. So, what is the difference between them? It all comes down to the label for overall energy change. Look closely at option A. The vertical arrow labeled overall energy change goes from the reactants line all the way up to the top of the curve. That is completely wrong. The energy from the reactants to the peak of the curve is actually called the activation energy. Now look at option B. The vertical arrow labeled overall energy change measures the difference between the starting energy of the reactants and the final energy of the products. This is perfectly correct. Therefore, B is our correct answer. Now let's tackle question 8.3. We are given the displayed formula equation between propane and oxygen. The overall energy change of the exothermic reaction is 2,219 kilojoules per mole. We need to find the missing bond energy of a carbon-hydrogen bond, labeled as X. This is a high-demand, 5-mark calculation question. Before we write down a single number, here is a golden tip from the examiner's report. Make sure you clearly label your working with words like bonds broken and bonds made. The examiners noted that many students missed out on marks because their pages were just a chaotic sea of additions and subtractions that were impossible to follow. Labeling your steps keeps your work clear and guarantees you pick up method marks. The energy change in a reaction is calculated by the difference between the energy required to break bonds and the energy release when the bonds are formed. Step 1 is to calculate the total energy required to break all the bonds in our reactants. Looking at the propane molecule on the left, we can see it contains carbon-to-carbon single bonds and carbon-to-hydrogen bonds. Be careful here. Count the lines between the carbons. There are exactly 2 carbon-carbon bonds, not 3. Since each carbon-carbon bond is 347 kilojoules, that's 2 times 347 equals to 694. Next, count the carbon-hydrogen bonds. There are 8 of them, so we write that as 8x. Finally, look at the oxygen. There are 5 oxygen-to-oxygen double bonds, so we multiply 5 by 498 to give us 2,490. Adding these together, 2 times 347 plus 2,490 gives us 3,184. So, our total energy for bonds broken is represented as 3,184 plus 8x. Writing this expression correctly secures your first mark. Step 2 is to calculate the energy released when new bonds are formed in the products. Let's look at carbon dioxide. Each carbon dioxide molecule contains 2 carbon-to-oxygen double bonds. Because there is a big number 3 in front, we have 3 times 2, which means 6 carbon-oxygen bonds in total. Looking at table 4, each bond is 805, so we calculate 6 times 805 is equal to 4,830. Now let's look at water. Each water molecule has 2 hydrogen-to-oxygen single bonds. With a big number 4 in front, that gives us 4 times 2, which is 8 hydrogen-oxygen bonds total. Each bond is 464, so we calculate 8 times 464. Adding these up, 6 times 805 plus 8 times 464 gives us a total of 8,542 kilojoules per mole. That is your second mark locked in. Step 3 is where a lot of students lost their footing. The question states that the overall energy change is 2,219 kilojoules per mole and emphasizes that this is an exothermic reaction. Because it is exothermic, it is going to be a negative value, therefore, energy change is minus 2,219. Let's plug in our values to break the bonds, 4,184 plus 8 times x, and subtract the values to form the bonds, 8,542. Setting up this equation correctly gives you your third mark. Now, we just use basic algebra to solve for x. If we rearrange to find the value of 8x, we get that 8x is equal to 8,542 minus 3,184 minus 2,219. This simplifies to 8x equals 3139. Finding this value earns you the fourth mark. Finally, to get x by itself, divide 3,139 by 8. This gives us 392.375. The mark scheme accepts this full value, or rounded to at least 3 significant figures, which is 392 kilojoules per mole. Write that down on the answer line to score a perfect 5 out of 5 marks. Let's start question 9. The introduction tells us this question is about acids and their reactions. Acids can be either weak or strong. Question 9.1 asks, what is meant by a weak acid? This is a fundamental definition question worth 2 marks, meaning we need 2 precise points to get full credit. Let's look at the exact wording required by the mark scheme and break down the specific chemical traps highlighted by the examiner. For our first mark, we need to describe what happens to the acid molecules. A weak acid is one that is partially ionized or partially dissociated. This means only a small fraction of the acid molecules split apart into ions when they interact with water. Now, be very careful with your grammar here. The examiner's report explicitly warns that some students incorrectly wrote that the acid is ionizing, implying it actively ionizes other species. You must state that the acid molecules themselves are ionized. Furthermore, do not say that the hydrogen ions are ionized or dissociated. The hydrogen ions are the result of the process, not the starting point. It is the original acid molecules that undergo partial ionization. For the second mark, we have to specify the environment where this takes place. This partial ionization happens in aqueous solution, which simply means when it is dissolved in water. The examiner noted that while over half of the students correctly remembered the term partially ionized to secure the first mark, many completely forgot to state that this happens in an aqueous solution. It's also vital to know that the second mark is fully dependent on the first mark. This means if you don't correctly state that the acid is partially ionized or dissociated, you cannot get the mark for mentioning the aqueous solution. To summarize, a perfect 2-mark answer that leaves no room for error is, a weak acid is an acid which is partially ionized in aqueous solution. Keep your chemical language precise, remember to include the solution condition, and you will secure both marks easily. Let's move on to question 9.2. The question asks us to explain what happens to the pH of an acid as the acid is diluted with water. This is a 2-mark question. Notice the keyword explain. This means it is not enough to just say what happens, we also need to provide the scientific reason why it happens. Let's look closely at how the marks are shared out. For the very first mark, we need to state the observation. When you add water to an acid, the pH increases. According to the examiner's report, 2/3 of students correctly realized the pH would change this way. However, some students missed out on this mark because they were too vague. They wrote that the pH would become closer to 7 without actually stating the direction of the change. Since acids have a pH below 7, moving closer to 7 means it goes up. But to get the mark, you must be explicit. Tell the examiner clearly that the pH increases. Now for our second mark, the why. Why does the pH go up? The scale of pH is a direct measure of how concentrated the hydrogen ions are in a solution. When you add water to the acid, you are increasing the volume of the liquid without adding any more acid particles. As a result, the concentration of hydrogen ions decreases. This decrease in hydrogen ion concentration is exactly why the solution becomes less acidic, pushing the pH upward. The examiner noted that far fewer students were able to articulate this reason correctly. To lock in this mark, make sure you use the key scientific term, concentration. Alternatively, you can say that the number of hydrogen ions per unit volume decreases, which the examiners also highly praised. To summarize, a perfect 2-mark answer is: Point 1. The pH increases. Point 2. Because the concentration of hydrogen ions decreases. Keep those 2 points precise, avoid being vague about the direction of pH, and those are 2 easy marks in the bag. Let's dive into question 9.3. The question sets the scene. A student does a titration to find the volume of acid needed to neutralize an alkali. The student fills a burette with the acid. Our task is to give 3 more steps the student must do before adding the acid to the alkali from the burette. We also must name any equipment used. This is worth 3 marks. Titration is a required practical, and the examiners are incredibly strict about the specific apparatus names and steps here. Let's look at the absolute must-have steps to get full marks. For the very first mark, we must measure out our alkali. The mark scheme explicitly requires you to state that the student must use a volumetric pipette to add the alkali. The examiner's report highlighted this as a massive stumbling block. Many students completely omitted this essential step, which instantly cost them full marks. When adding a fixed volume for a titration, always use a burette. Beakers and measuring cylinders do not have the accuracy required. To get our remaining 2 marks, we can choose any 2 correct steps from the following pool. First, the alkali must be added into a conical flask. The examiner's report notes that carrying out a titration in a beaker will not gain credit due to the risk of spillage while swirling. Second, we need to add an indicator to the alkali. But beware of a massive trap here. You can name a specific indicator like phenolphthalein or methyl orange, but you must not accept universal indicator. The examiner notes that universal indicator changes color too gradually, making it completely unsuitable for detecting the exact endpoint of a titration. Third, you can state that the student must take the initial burette reading. If you write this, make sure your phrasing is precise. The examiner pointed out that many students express themselves poorly, forgetting that a burette gives a reading of volume, not a reading of amount. Finally, you can mention the use of a white tile under the conical flask, which helps you clearly see the exact moment the indicator changes color. To wrap this up cleanly and guarantee your 3 marks, here is the perfect, foolproof sequence to write down. Number 1, use a volumetric pipette to add the alkali. Number 2, transfer the alkali into a conical flask. Number 3, add a few drops of a named indicator, such as phenolphthalein. Avoid the beaker and universal indicator traps, use the correct equipment names, and you've got full marks secured. We move to question 9.4. The question states, the student titrated a solution containing 0.00 for 5 moles of sodium hydroxide with 0.15 moles per cubic decimeter hydrochloric acid. We are given a balanced equation, sodium hydroxide plus hydrochloric acid reacts to form sodium chloride and water. The goal is to calculate the volume of hydrochloric acid in cubic centimeters needed in the titration. This is worth 2 marks. Titration math can seem intimidating, but if we break it down step by step and keep an eye on our units, it's very straightforward. Let's plug in our numbers. Our moles of sodium hydroxide is 0.0045. Because the balanced equation shows a 1-to-1 reacting ratio, we also need exactly 0.00 for 5 moles of hydrochloric acid. We divide this by our acid concentration, which is 0.15. Doing the math, 0.00 for 5 divided by 0.15 gives us 0.030 cubic decimeters. Stating 0.030 cubic decimeters secures your very first mark. For the second mark, we have to fulfill the final requirement of the prompt, converting the volume into cubic centimeters. To convert cubic decimeters to cubic centimeters, we multiply our value by 1000 because there are 1000 cubic centimeters in a single cubic decimeter. So, we take 0.030 and multiply it by 1000. This gives us our final answer of 30 cubic centimeters. Writing 30 on the answer line locks in the second mark. Let's look at the absolute final question on the paper, question 9.5. The prompt gives us a key piece of information: a calcium atom is larger than a magnesium atom. The question asks us to explain why calcium reacts more vigorously than magnesium with hydrochloric acid of the same concentration. This is a high-demand, 3-mark question testing periodic trends. The examiners noted it discriminated very well, with fewer than a third of students scoring all 3 marks. Let's break down how to craft a chemically precise, top-tier answer. To understand this trend, we need to think about what happens when metals react. Metals react by losing their outer shell electrons to form positive ions. For our first mark, we must look at the physical distance. Because calcium has more shells, calcium's outer shell electrons are further from the nucleus. You can also say calcium has more energy levels. For the second mark, we connect this distance to electrostatic attraction. Because those outer electrons are further away, the outer electrons are less strongly attracted to the positive nucleus. You could alternatively state that the outer electrons are more shielded from the nucleus. Finally, for the third mark, we link this attraction back to the rate of the reaction. Because the attraction is weaker, positive ions are formed more easily, or you can say electrons are more easily lost. That ease of losing electrons is exactly why calcium reacts much more vigorously. Now let's look at the examiner's report, because imprecise vocabulary cost plenty of students their marks here. First, you must specify which electrons you are talking about. Writing electrons are further away without explicitly saying outer electrons or outer shell will not gain credit. Second, you must clearly define the force involved. Saying the force between the outer electrons and the nucleus is not enough, you must specify that it is an attractive force, and that this attraction is weaker. Also, a shocking number of students incorrectly describe the force between the nucleus and the outer electrons as intermolecular. Remember, intermolecular forces only exist between separate molecules, not inside a single atom. Some students mentioned more outer shells. This is not correct because outer is always taken to mean the one shell furthest from the nucleus. Finally, do not get confused between atomic structure and surface area. Some students saw the word a larger and tried to argue that calcium had a larger surface area like a lump of metal. The question is explicitly talking about individual atoms. Keep your focus entirely on atomic structure. And that brings us to the very end of the June 2020 AQA GCSE Chemistry Paper 1 walkthrough. Thank you so much for watching. If you found these detailed breakdowns and examiner insights helpful, please hit that like button, leave a comment if you have any questions, and subscribe to the channel so you don't miss our upcoming papers walkthroughs. If you are looking for a dedicated online chemistry tutor to help you build confidence, master your exam technique, and secure top grades, I am here to help. I have left a link to my tutoring website in the description below, so be sure to check that out to book a session. Best of luck with your revision, keep working hard, and I will see you all in the next video.